In the last video, you learned about what the Snowball Earth hypothesis actually was and about the factors that cause this phenomenon to occur. In this video, we're going to look at the evidence that scientists have found to support the theory that the Earth was completely frozen over millions of years ago. The first line of evidence that scientists have found is dropstones. Dropstones are stones carried out in bodies of water by glaciers. These isolated fragments of rock are found within sedimentary rock strata on the ocean floor. When glaciers melt, the dropstones are deposited in ocean sediment and are incorporated into sedimentary rock. Scientists have uncovered a vast amount of dropstones dated to the Neoproterozoic era, when the Snowball Earth is hypothesized to have occurred. These dropstones have been found in great uniformity and extent around the world, including in strata layers containing carbonate rock, which can only form under warm conditions. These findings indicate that the rock was laid within the tropics when the dropstones were deposited. Since dropstones can only be created by glacial activity, they serve as evidence that ice during the Snowball Earth actually reached the tropics. The next line of evidence that we're going to discuss is glacial deposits. There are two types of glacial deposits, glacial till and glacial erratics. Glacial till refers to uneven rocks of varying sizes that fall off the sides and back off glaciers in localized clusters. Glacial erratics, on the other hand, specifically refer to large boulders that have been transported by glaciers and left behind once the glacier melted, embedding themselves in the local bedrock. These deposits differ from the local rocks in the area that they were found in. Therefore, it can be concluded that they must have been transported from another location. Glacial deposits have been found in Norway, Greenland, Australia, and Namibia, where the latter two being close to the equator, and Australia in particular being 10 degrees away from the equator during the glaciations. So why is this important? Glaciers leave behind glacial deposits in places that they once existed in, which means that all of the above places must have contained glaciers at one point. If all of these places have varying latitude containing glaciers, then it is very likely that the entire Earth did, supporting the Snowball Earth hypothesis. A few other possible explanations exist to explain the formation of these deposits. However, none of them would have actually been able to create such deposits. These rocks are most likely not sedimentary in nature because sedimentary rocks have smoother surfaces, having been weathered by constant flowing water, while glacial deposits have uneven and jagged edges due to having fallen straight off the glaciers without being eroded. They also have not been caused by landslides, as glacial deposits are localized and are left in clear piles, while rocks dislodged during landslides are more spread out. Finally, glacial erratics cannot be attributed to strong currents or even icebergs, as these aren't powerful enough to move such large boulders. The only explanation left for the occurrence of these deposits, therefore, are glaciers.
Paleolatitude determination. Furthermore, scientists have utilized paleomagnetism to confirm that global glaciations have occurred in the past. When sedimentary rocks form, their iron, nickel, and cobalt particles align with the Earth's magnetic field, forming field lines. By examining and measuring the direction of these field lines, scientists can determine the original location of these ancient rocks. For example, rocks at the poles form vertical field lines, while rocks deposited at the equator have horizontal field lines. Scientists have found glacial deposits dated to the Cryogenian period, which formed near the equator. Since the sedimentary rock also contained glacial dropstones, scientists determined that ice during Snowball Earth did, in fact, reach the equator. If ice covered the warmest latitudes on the planet, then it is more certain that the entire Earth was indeed glaciated. Isotopic geochemistry. The basic concept of isotope geochemistry is that the ratio of two isotopes of the same element is affected by major environmental changes, and deposits of these isotopes that form will reflect the environmental conditions present at the time that they were created. An element of relevance to the Snowball Earth hypothesis is carbon. Carbon has two stable isotopes, carbon 12 and carbon 13. Carbon 12 makes up about around 1.1% of all naturally occurring carbon atoms, and carbon 13 makes up the rest. While they are very similar, carbon 13 is heavier than carbon 12, so plants prefer to intake carbon 12 due to it being easier to transport in their structures. During the glaciations, global plant life was almost completely extinguished due to the extreme cold and harsh weather conditions, so carbon 12 was no longer being preferentially removed from the atmosphere. So, the ratio of carbon 12 to 13 would be higher than usual because there would be more carbon 12 in the atmosphere. A drop in carbon 13 in glacial deposits near the tropics suggests that there was a drop in biological activity at the time that Snowball Earth is thought to have occurred. If there was a huge decrease in plant life spanning all the way to the equator, it would have been due to a worldwide glaciation, further supporting the Snowball Earth hypothesis. Banded iron formations. The last piece of evidence that we're going to discuss is banded iron formations, but we're first going to look at how they form. Oceans were thought to have been iron-rich in the past, and if oxygen levels rose in the atmosphere, the iron in the water would oxidize and precipitate out as iron oxide, forming banded iron deposits in the bedrock. However, if oxygen levels dropped significantly or the water's access to the atmosphere was removed, iron would stop precipitating out, and the bedrock formed during this time would be iron poor. Banded iron formations are rare, first appearing around 2.4 billion years ago, when oxygen produced by photosynthesis precipitated all oceanic iron out. However, they reappear around 750 million years ago, which is coincident with Earth's glaciation events. During the actual glaciations, no iron bands would have formed due to the ice cover blocking off the water's access to atmospheric oxygen. However, once the glaciations had ended, the oceans would be exposed to a huge spike in atmospheric oxygen, creating a set of banded iron formations. The spike in oxygen levels is thought to have been due to an increase in nutrients essential for algae, which caused their populations to increase and which therefore led to an increase in oxygen. These particular banded iron formations have been observed in many places globally, but not all, since their formation requires a special set of geological conditions. While hydroxides have the ability to precipitate iron out as oxygen does, oceans in the past were quite acidic. This was due to a higher concentration of dissolved carbon dioxide. Cooler oceans can hold more carbon dioxide, and the oceans were cooler because of a fainter sun, as the sun increases in power output over time. Therefore, it is quite certain that the oxygen exposure after the glaciations precipitated the iron out, and not hydroxides. In summary, the key lines of evidence for the Snowball Earth hypothesis are dropstones, glacial deposits, paleolatitude determination, isotope geochemistry, and banded iron formations.